We continue with section 2.5, and in this video we're going to talk about properties of the determinant. We might have noticed that calculating a determinant of a matrix is extremely taxing in terms of the number of computations you have to do to get the determinant. And the strategy that we have so far is to expand the determinant along the row or a column that contains the most zeros. But if we don't have many zeros in our rows or columns, then we don't really have any strategy other than to just calculate the other than just doing all the calculations that we have to do. So in this section we are going to discuss some methods to reduce the number of calculations involved in evaluating the determinant of a matrix. So suppose you've got an n by n matrix A which is in row echelon form. Then you will notice that if A is like the example that we have, in this example we took it from exercise 2.5.2 number 6D. You will notice that the determinant of A will, if we expand the determinant using the first column, or according to the first column, these are just zeros, so therefore we just need to find the determinant of A. We have to find the determinant, so we say A times the remaining matrix, which is left with this 3 by 3 matrix there. So we will see that we have A times the determinant of the remaining matrix, and then again if we multiply by, if we expand according to the first column again, we find out that we've got E times the remaining matrix after removing column 1 and row 1, and that is HI0J, and then its determinant is obviously HJ. So we find out that the determinant is just the product of the diagonal entries of the matrix. Right, so we can see from this that it is much easier to calculate the determinant of a matrix in row echelon form compared to that of a general matrix, which might not be in row echelon form. And we also know that every square matrix is row equivalent to a matrix in row echelon form. So that tells us that if we are able to reduce our matrix to row echelon form, and we know how elementary row operations affect the determinant of a matrix, then we will be able to exploit this fact that it's much easier to find the matrix, the determinant of a matrix in row echelon form. And so we are going to find out how row operations affect the determinant of a matrix, and this is theorem 2.5.14. So let A be a square matrix, then the following statements are true. If a multiple of one row of A is added to another row to produce a matrix B, then the determinant of A is equal to the determinant of B. So this row operation is where we say Ri goes to Ri plus Srj, where S is a non-zero real number, and we find out that the determinant of A is not actually affected by this elementary row operation. Now the second one says if two rows of A are interchanged to produce a matrix B, then the determinant of B will be equal to minus the determinant of A. Right, so this is our Ri interchange with Rj, and we see that the determinant of the new matrix is minus the determinant of our original matrix. And if one row of A is multiplied by a scalar k to produce a matrix B, then determinant of B is equal to k times determinant of A. So this is very good information, because now we can reduce our elementary row operations and then see how the elementary row operations affected our determinant, and find our determinant. Right, so let's illustrate what we have just been told in this theorem with an example, and this is example 2.5.15. So suppose you've got a matrix A like that. Now its determinant, so if you expand using the first column, you find out that determinant is equal to -2, right? And so we want to check, apply the different row operations to see how they will affect the determinant, and solidify our theorem with this example. Right, so apply the row operation R3 goes to R3 minus 3R2 to obtain the matrix B. So this row operation is the one in the um, first part of the theorem. So we are told that the determinant of A is equal to the determinant of B. So we are expecting that the determinant doesn't change. So if we expand according to the first column, we get, so here we can see that because it's in row echelon form, the determinant is just the product of the entries in the main diagonal, and that gives us -2. And this is obviously what we found for determinant of A. So determinant of B is equal to determinant of A, as we expected. Now let's do a row interchange. So that is the second example here. And so if we do a row interchange, and we calculate the determinant of B, and by expanding according to the first column, we see that the determinant of B is equal to 2, which is equal to the which is equal to -2, which is minus the determinant of A, which is what we were told in the theorem. Now let's go on to the last, where we do scalar scaling of a row. So apply R2 goes to 3R2 to A, we get that. And then if we do the, if we apply, sorry, if we find the determinant, we can expand according to the first column, and we find out that this is equal to -6, which is equal to 3 times -2, which is equal to 3 determinant of A. So that K is what we see there. So this affirms that, well, using this example, we have verified that indeed the theorem, even though we don't have the proof, but we have seen that this example is consistent with this theorem. Right, now it turns out that if we do some column operations which are performed the same way that we do row operations, then this theorem also holds. Right, so and this is theorem 2.5.16 in the textbook. Let A be a square matrix. Then the following statements are true. If a multiple of one column of A is added to another column to produce a matrix B, then determinant of A is equal to determinant of B. So in other words, if we say Ci goes to Ci plus SCJ, where S is a non-zero real number, then the determinant of A is not affected by that elementary row operation. Now, and if we do a column interchange, that is 2, then determinant of B will be equal to minus determinant of A. And if we scale a a column, again we get determinant of b is equal to k times determinant of a. Now so that helps us because sometimes working with columns might be easier than working with rows. So we're going to look at an example and to illustrate these two theorems. So, or not illustrate, but to actually find determinants of matrices using these two theorems. So if we look at example 2.5.17 in the textbook, we can see that the determinant of A, we want to find the determinant of A. We note that we have a 2 there and a minus 2 there. We've got a minus 8 there and an 8. So if we add, so if we say R1 goes to R1 plus R2, this becomes 0, that becomes 0, and then that becomes minus 5. So therefore we've got 0, 0, minus 5, and then we can expand using the first row. So if we apply R1 goes to R1 plus R2, we get this matrix, and then we can expand using the first row. So we get 0, 0, and then we find the determinant of we find that minus 5 times the determinant of the remaining 2 by 2 matrix, and then we find that the matrix that the determinant is equal to 30, right? And because the elementary row operation that we used here, R1 plus R1 goes to R1 plus R2, does not affect the determinant, we know that determinant of A is equal to determinant of B, which is equal to 30. Now let's look at another example, and this is 2.5.18. So we want to find the determinant of B, where B is equal to this, and so we do a bunch of elementary row operations. So here we make that a 0, we make that a 0 using these ones, and then we scale this R3, and then we do more row operations, and we end up with a matrix in row echelon form, right? So so now we look at the elementary row operations that were used, and we find out that these ones don't affect our so these ones don't affect our determinant. This one affects our determinant. These ones don't affect our determinant. So therefore the only row operation that affects our determinant is this. And what does it say? According to theorem 2.5.40, part 3, determinant of C, which is the matrix in row echelon form, is equal to 3/4 of determinant of B. So therefore determinant of B is 4/3 determinant of C, and then we find determinant of C by multiplying all the entries in the main diagonal, and we find out that this is equal to minus 36. Right, let's look at another example. So we've got a 5 by 5 matrix that we have to find its determinant. So if you look closely, you'll see that the fourth column is a sum of the second and the third column. 1 plus 3 is equal to 4. 2 minus 1 is equal to 1. 3 plus 1 is equal to 4. 2 plus 2 is equal to 4. 1 plus 3 is equal to 4. So if we do a column operation which says C4 goes to C4 minus C2 minus C1, we get we obtain this matrix B, which is equal to this, where the fourth column is a column of zeros. So if we expand according to that column, the fourth column, we know that the determinant is equal to 0, and because the elementary row operation that we used does not affect the determinant, then the determinant of A is also equal to 0. Right, let's look at more properties of determinants. So let A and B be n by n matrices, and let K be a real number. And this is theorem 2.5.20 in the textbook. Then the following statements are true. The determinant of Ka is equal to k to the n determinant of A, and determinant of AB is equal to the determinant of A times the determinant of B. And so we are going to illustrate theorem 2.5.20 part 2 with an example, right? And the proof of one is left as an exercise 2.5.2 number 9 in the textbook, right? So let A be equal to the matrix given and B be that, then AB is equal to, so if you do the matrix multiplication, you can verify that AB is equal to that. And determinant of A is equal to minus 6. You can do the calculation. Determinant of B is also 3. And so if we find the determinant of AB, we will see that the determinant of AB is equal to minus 18, which is equal to minus 6 times 3, which is equal to determinant of A and determinant of B, which we expected from using theorem 2.5.20, right? So if we look at this, we see that determinant of AB is equal to determinant of A times determinant of B. But however, determinant of A plus B is not equal to the determinant of A plus the determinant of B. And and we're going to illustrate this with a counterexample, 2.5.22, and it's, so we have A as that and B as that and A plus B as that. So you see that determinant of A is 1, determinant of B is 1, and determinant of A plus B is 0, which is not equal to the 2, which is the 2 being the determinant of A plus determinant of B. So therefore that is not true in general. Thank you. We'll continue with the last part of section 2.5. Thank you.